uses with scheduling. So this is a joint work with MIT, Cornell, Intel Labs, and Columbia University. So before going to the talk, let's talk about why tail latency is an important concept and why it's even harder to manage with new programming paradigms like microservices. So what is tail latency, and why do we care about it rather than average? The right way to understand the latency of the system is by percentile. This is because since one slow request might take 10 to 100 times longer than the median, an average gives a fairly meaningless number. And in microservices, that tail latency in a single service could propagate across all dependent service tiers. Let's do a simple calculation. If there are 100 machines, the probability of hitting the P99 latency on one machine is more than 60%. So it's becoming increasingly important. As tail latency can significantly impact the revenue and user experiences. For example, at Amazon, every 100 milliseconds of latency causes a 1% decrease in sales. A broker could also lose more than $4 million in revenues per millisecond if their electronic trading platform is 5 milliseconds behind the competition. So by minimizing tail latency, we can improve user satisfaction, increase sales, and improve service resilience. Let's dig deeper into one of the reasons for high tail latency. Due to the high level of multi-tenancy brought by microservices, applications are sharing cores, PCIe bandwidth, cache, memories, etc. And it makes scheduling for microsecond scale applications even harder. Here, I randomly sampled 4 warehouse scale computing applications in Google data center workload traces on a random day and calculated the average thread per core. So for each application, the number is more than 50%. What does it mean? So if the minimum scheduling time quantum is 5 milliseconds, which is lower than the kernel scheduling time quantum already, and if there are 200 threads on average per core, the scheduling cycle will be increased to 1 second, significantly increasing the tail latency. Obviously, existing kernel scheduling paradigm is not able to satisfy our goal. So how do we manage tail at scale? One of the existing solutions is to design specialized data plane operating systems that can directly manipulate the hardware to improve the performance. For example, Shinjuku was able to directly access hardware APIC timers to issue fine-grained preemption to worker threads. The philosophy of general data plane operating system is to put the complexity of OS stack into a container-like layer in week 3. Although these systems provide good performance, their kernel implementations cannot be easily changed and are costly to maintain, and they are often incompatible with existing applications and security concerns. And the question we have is, can we really build a scheduling system that does not rely on non-standard use of hardware but still provide good performance? So in this talk, I will introduce the preamble. Tailored to different workload service time, we propose new scheduling abstractions and enabled new policies for flexibility, security, portability, and performance. So I'd like to talk a little bit more about 2 different paradigms of scheduling under unknown service time. Our goal here is to reduce the latency and improve the microsecond scale workload with scheduling. So here we show a centralized first come first served scheduler without any preemption. And when the jobs are of various sizes, the longer job will block the shorter ones, causing head-of-line blocking. However, if we issue preemption, it reduces the tail latency. For example, although the scheduler doesn't know the ground truth execution time, but by switching the order of the blue requests with the shorter ones after a specific quantum, it can improve the shorter request latency by reducing the queuing with a specific context switching overhead. So to understand why the current fixed preemption policy class is not enough, let's look at the low latency plot of a database query. Due to the high dispersive nature of the requests, preemptive scheduling policy works better under lower load because it reduces the head-of-line blocking as we have mentioned before. However, because of the overhead involved in frequent context switching, under higher system load, non-preemptive policy achieves higher throughput and lower latency. So the key insights of our system design is that we need an adaptive and microsecond scale preemption policy in order to achieve efficiency and performance at all loads. The existing implementation of preemptive scheduling system usually involves 2 schemes in terms of ownership. Kernel space managed solutions like Shinjuku are generally faster due to their direct access to the hardware preemption. However, it has portability issues. On the other hand, user-space managed solutions stand out in its flexibility and low deployment effort. However, it can be much slower for preemption. For example, externally pausing time code and transferring control to a scheduler runtime, a scheduler routine like what the Goku routine and Lebeaver did is very costly. So how do we tame this seemingly impossible trade-off between performance and portability and achieve the desired adaptiveness required by the application? The answer is a cross-stack scheduling solution. Our proposal is to leverage hardware to facilitate fast preemption while still utilizing user-managed abstractions for scalability, security, portability, and all the other requirements. So generally, how do we design an efficient scheduling system for microsecond scale apps? There are three different layers. On the policy side, there are cooperative and fixed preemption policy. And the software-centric solutions usually propose different runtimes like centralized or decentralized first come, first serve. Hardware-centric solutions, on the other hand, propose different communication protocols that we can use. For example, PaaS solutions like Nebula or NanoPU propose cache coherence or direct register. LibPreemptible expanded the existing design paradigm. We introduced adaptive preemption policy, a scalable and secure runtime on software, and a low overhead preemption mechanism based on hardware user-level interrupt. Thus, it addresses the software and hardware gap and achieves fast, portable, and adaptive library. So to understand our design and how to harmonize the hardware mechanism with software requirements, let's begin with an overview of a general scheduling system. The system typically consists of two main components, the network subsystem and the request scheduling subsystem. Our focus is on the latter, represented by the red box. The network system can be implemented using various optimizations, including DPDK or kernel bypass solutions. So let's zoom into the request scheduling subsystem. So usually it is composed of multiple different run queues in the runtime and worker threads. The scheduler will decide on when and where to schedule the incoming requests onto different workers and cores. For example, here the scheduler launches execution of the longer task in the queue. After some time, a shorter request comes and we see that the longer task caused the header point blocking again. So how do we preempt? Usually, if the longer job does not have a voluntary yield, the scheduler will rely on some external timer mechanism for preemption. We see that if the preemption is faster and the lower the overhead, we can get better tail latency and efficiency. However, doing this adaptive preemption efficiently without knowing the request service time is challenging. Let me show you layer by layer of the software stack overview of the preemptible library to achieve these goals. On the top level, applications can bake their QoS requirement into the scheduler. And in the middle layer, the scheduler will decide on the time quantum to execute and preempt the requests. Below that, the API enables fine-grained deadlines based on the scheduling decisions for each request at microsecond scale. It provides the data structures for collecting statistics of past requests, including the latency and different nodes, waiting times, etc., which is useful for the scheduler to make adaptive quantum control decision. Further down the layer, we design a new abstraction called Libut timer to adjust the timer deadlines according to the LibPreemptible API and fire interrupt to preempt worker threads. So there can be multiple applications using LibPreemptible in their own address space. So let me show you some of the details of different layers. At the bottom layer of our library, we address the challenge of good performance at microsecond scale with low overhead interrupt, all in the user space. So the key mechanism we use is user interrupt, which is a new hardware capability that delivers low overhead preemption without any kernel mediation. User interrupt avoids transitioning through the kernel by sending and handling hardware interrupt directly in non-privileged applications. In comparison with traditional mechanisms like signals, it achieves much lower time slices and overhead. Hence, we can build a periodic user-level timer based on this faster way to signal, with much finer granularity compared with the kernel timers. The mechanism can be decomposed into two different phases, setup and delivery phase. In the setup phase, receiver set up UPID and register the handler, and return the user interrupt file descriptor to the sender. Senders uses the file descriptor to allocate UITTE and get the UIPI index. In the delivery phase, senders call send UIPI instruction. However, user interrupt only provides the mechanism and it's not relevant to scheduling. So how can we make it useful for scheduling, especially for various applications? The runtime design tackles the portability and scalability challenges. The runtime of our scheduling systems includes the data structure, the preemptible with user-level threads and user timer. Compare with traditional polling-based mechanisms that sacrifice efficiency for tail latency, and compare with solutions that directly maps APIC timers to the same dispatcher address space that sacrifice security for performance. Libut timer instead leverage dedicated timer addresses and user interrupt and wait instructions to achieve better efficiency and scalability at the same time. The security is achieved by design since each application owns their timer in different address space separately. Now let me show you how we design the APIs to achieve portability to different applications. Here is a timeline of the request being served in function F. After using the API FN worker register that we designed, the function execution begins immediately after we call FN launch, and it gets preempted after the timeout microsecond specified by the argument. FN completed checks the status of the preemptible function. It returns 0, which means that the function needs to be rescheduled. FN resume can be called by the scheduler with similar argument for a function pointer and a timeout. The scheduler then decides on the other requests to schedule and changes timeout value accordingly when the earlier requests get preempted. When the function finishes, FN completed will return 1, and we can call FN worker and register to release the stacks, deadline addresses, etc. Now I will demonstrate how this abstraction and API combined can enable more powerful policy classes than traditional scheduling systems. The adaptive policy will manage the trade-offs we mentioned between efficiency and performance. Earlier we have seen that preemptive policy and non-preemptive policy have different trade-offs in efficiency and latency. However, I'm going to show you in a real system, to minimize tail latency, it's even harder since the design space within preemptive policy can be very complex. We have two universes to talk about workload service time distribution in the data center. Note that this is a random variable which can either fall into heavy-tailed or light-tailed schemes. For one, when the job is heavy-tailed, the response time decays polynomially in T. For another, when the job size is light-tailed, the response time decays exponentially in T. The two terms of interest are C and gamma, which is the tail constant and decay rate. So when we talk about optimal scheduling policy, we want to optimize the C pi and gamma pi and the policy pi. Under the idealized system, without any preemption overhead and post-arrival rate, etc., we know that FCFS, first come first served, is optimal for light tail, while process sharing is optimal for heavy tail. However, in the real system, it's never ideal, and preemption has overhead. These two figures show an experiment with two types of workload service time distribution with overhead as 1 microsecond. The x-axis shows the percentage of max load of the system, and y shows the tail latency. Different legends show the preemption quantum. As illustrated in the green bars, for light-tailed workload, higher time quantum gives better tail latency overall. For heavy-tailed workload, lower time quantum gives better tail latency until the quanta is too low and the overhead eliminates the benefit. So the tail optimal scheduling policy not only varies with the request service time distribution, but also depends on the system, including the preemption overhead and the workload. So how do we do adaptive quantum control? To tackle challenges of unknown service time and non-idealized system, we use statistical learning and control. In one of the dynamic quantum controller design, we take the target latency, the notion of the load, and feed that into the system. In the meantime, we collect tuning statistics and leverage statistical learning to fit the tail index, which helps us identify service time distribution shift. Then we use feedback control to change the time quantum in a way that adapts to the dynamic change to satisfy the SFO of the workload. So putting things together, here's an example. The scheduler will pick up the first request from dispatch queue to run on worker thread with the initial time quantum that the user set with it in launch. However, as the requests are lighter tailed and come at low load, the scheduler will relax the time quantum to a larger value to meet SLO without unnecessary preemption overhead. Now, at t equals to 4, a latency critical task comes. However, there's no additional worker for that task. The statistical learning module further identified that the distribution shifted from light-tailed to heavy-tailed, and it would decrease the time quantum to a smaller value to avoid head-of-line losses. Then the scheduler will preempt the longer request and picks up the next element from the dispatch queue, thereby giving preemption priority to the shorter jobs. If the dispatch queue is empty, the scheduler resumes previous preempted requests from the longer queue via FMAC calls. If the dispatch, so basically, we can see that under this scheme, we can dynamically change the quantum according to the incoming request. So to sum up, the preamble achieves the following design features: fast, adaptive, secure, portable, and scalable. Some of the details can be found in the paper. So now let me show you some of the evaluations. We compare with baseline Shinjuku and Lebinger. First, we want to evaluate the performance. If we compare the preamble with the prior state of art, we have a total benefit around 10 times in the low latency position here and the high load. To separate benefit from the new hardware, we disable the user interrupt. Because the signal-based timer's granularity and overhead is much larger, the tail latency and the high load worsened by more than 5 times. However, it is still better than baseline. This is because of the adaptive time quantum controller. Under lower load and lower dispersion, the time quantum is set to a higher value, consuming fewer CPU cycles for preemption to improve the overall efficiency and performance. In this experiment, we show another use case of the preamble in real-world applications. To improve resource management and enable efficient CPU utilization, latency-critical jobs can timeshare CPU resources with best effort jobs and use preemption to reclaim resources adaptively. This reclamation must happen adaptively in microsecond scale to ensure low tail latency when needed. Achieving this is very hard, especially for jobs with sub-microsecond scale SLO requirements due to the large context switching overhead. However, with the preamble, this overhead is reduced, and we achieved 4.4 times tail latency improvement, only at the cost of 1.2 times BE throughput, which is a more favorable trade-off than baseline systems. One of the key contributions of the preamble API is the ability to set the preemption interval on a per request basis dynamically. In this figure, we show a different workload pattern with multiple load spikes at t equals to 3 and 6 seconds. With a fixed preemption of 10 microsecond policy, we compare with the black non-preempted version, it achieves a much better LC latency at the cost of BE throughput. With a larger fixed preemption quantum of 50 microsecond, we have a better BE throughput but sacrifice LC latency. However, with dynamic quantum, we can adjust the quanta according to the load and achieve the best of both worlds. So there are more sensitivity studies, macro benchmarks, discussion about security in the paper. Due to time constraints, I will skip this. And there are some future extensions, including scheduling and reallocation about the cores across different applications, and doing intelligent scheduling for emerging applications beyond microservices like large language models with this adaptive preemption policy, and adding dynamic work stealing policies with fine-grained preemption and late binding across different stacks. So this concludes my talk. In summary, the preamble is a hardware-assisted user-level preemptive scheduling library. It achieves adaptive scheduling policy, fast mechanism, and portable runtime. With that, I'm happy to answer any questions, and thank you very much for listening and your attention.
Thank you for your presentation. So I have two questions. One is, maybe I missed it, but did you evaluate this on a real platform? Sorry, like Sapphire Rapids, that supports user-level interrupts?
Yeah, so the full system is built on U platform with Intel SPR machine. So all the experiments we did is not on simulators, on real system. So if you are interested, I listed the hardware software setup here, and there are specific network stacks we use and Linux kernel versions we use.
Okay.
Yeah.
The second question is that so in this work you basically use the message passing approach where you have one scheduler running on a particular core and then it sends these interrupts to other worker threads. But then are you familiar with this recent work in SOSP23 where they still use shared memory approach where the scheduler basically sets a variable which the other threads poll on, so it reduces the overhead for the scheduling. Would you care to comment on that?
Yeah, this is a good question. If I understand you correctly, the SOSP23 paper is actually